So let's take a look now at our active band reject filter. So in the plot down here below, we can see the basic properties that we want. We want our frequency to be blocked between our two 3 dB frequencies, omega 1 and omega 2. So omega 1 and omega 2 are where we're at our maximum value of gain k divided by square root of 2. So of course that's the same thing as multiplying by 0.707 approximately. And if we're in between those two frequencies, we're wanting to block the frequencies. If we're outside, we're below omega 1 or above omega 2, we want to be passing those frequencies. So we can see well below omega 1 we have a gain of k, well above omega 2 we have a gain of k, and then at our center frequency omega 0 we have our minimum gain, which we've not specified a value, but we'll come back at the end of the video and write at least what that value is. So one way that we could achieve this sort of behavior is we could take that same configuration, that same cascade configuration for our active band pass filter, and just adjust our frequencies omega 1 and omega 2 such that omega 1 from the high pass filter is greater than omega 2 for the low pass filter. But what we're going to do is we're going to consider a different configuration just so we get exposure to sort of some different ways to do this. So let's start by looking at a basic block diagram of what we want to do. So we want to have a low pass filter, which is setting omega 1, and a high pass filter, which is setting omega 2, sort of operating in parallel. So we have an input voltage that goes into each of those. Each of the outputs from our low pass and high pass filter is then fed into a summing amplifier to give us our overall output. So what we can think of is our low pass is taking a portion of the signal and blocking the high frequencies. Our high pass is taking a portion of the signal, blocking the low frequencies, and then we're combining the output of those two filters together. And so again, because our summing amp is technically an inverting configuration, really we should have a negative here, but the basic idea is we're adding these two signals. And we're also going to see we have a scaling factor depending on our amplifier. But the basic idea again is that we're adding the two outputs. So let's see how we can do that using our basic low pass and high pass active filters that we have discussed before. So here is a circuit realization of that block diagram. And so again, we have sort of three key components that we can look at. So down here in the bottom, we notice we have our high pass. And so this is high pass because we have that capacitor in our input impedance. Up here in the top, we have our low pass configuration because our capacitance is in the feedback network. So this is low pass. And so one thing I failed to mention in the previous video, which maybe some of you caught on to, is because in these low pass and high pass filters here, because these R values are the same, when we go to write the transfer functions, we're not going to have an RF over I term because that value is just 1. So that's why that term, you might think it's missing, but it's not, it's just 1 for this case. So the third part, of course, is our summing amplifier on our output. And so this is the same configuration that we have seen back in our op-amp unit. Notice we have two inputs going through the same resistance value, Ri, connected to our inverting input, and then a feedback resistor, Rf. So we can write the overall transfer for this function. Essentially what we can do is we could identify our output voltages as I've labeled above V1 and V2, and then treat those as inputs to our summing amplifier. So sort of doing that in one step, we can say our transfer function is h of j omega is equal to negative Rf divided by Ri. And so that's coming from the inverting amplifier on the summing junction. So we have negative Rf divided by Ri for both cases. So I've just factored it out front. And then that's going to be multiplied by the gain of each of these stages going from our input to V1, for instance, and our input down here to our V2. So for our low pass filter, we have negative 1 over 1 plus j omega C1R. And then for our high pass, so we're subtracting j omega C2R divided by 1 plus j omega C2R. So we get this for our transfer function. And so again, because we're talking about band pass, the same applies for band pass and band reject. So same equations from our series resonance are going to apply here. Same equations from series resonance apply. And so those are the equations for our omega 1, our omega 2, our omega naught, our B, and our Q. And so we should note that we set our omega 1 and omega 2, and so let me take a step back and say we can't necessarily use all of the equations that we had for the series resonance. So for instance, we couldn't use our omega naught equation that's based on resistance and inductance, or rather inductance and capacitance, because of course we don't have an inductance here. So we want to use the equations for omega 1 and omega 2 for our corner frequencies based on these values here, like we saw in the previous video. So it'll be 1 over C1R1 and 1 over C2R2. And then once we know omega 1 and omega 2, we can use other equations that use those values to get our other three values. For instance, our B would just be omega 2 minus omega 1, omega naught is square root of omega 1, omega 2, and so on. And so we did talk about those equations when we looked at our active bandpass filter, so you can look there as well. Looking at this transfer function, it's a little easier to analyze than it was for our bandpass filter. So we can say as our frequency is going to 0, we can determine what that maximum gain value K is. So we can actually do that for omega goes to a 0 and omega goes from infinity to infinity based on our behavior. And again, we're just considering these values of omega here. So let's, for instance, consider the case of 0. So if we have the case of 0, over here on our right term, we're going to have 0 divided by 1 plus 0, so that's going to go away, that's just 0. And in our left term, we're going to have negative 1 over 1 plus 0, so we'll just have a negative 1. And so the negative 1 will cancel out with that negative in our RF over RI, and we're going to get that our gain K is just equal to RF over RI. And so again, this is for this particular configuration. We could also find the gain at this center frequency. So we could find the gain at this level here. We're not going to go through that, but what we could do is we could evaluate, we could find the magnitude of H at j omega naught, and then of course we have to keep in mind that our omega naught is square root of omega 1, omega 2. We use those definitions for omega 1 and omega 2 that relate them to R and C. And if we go through a process similar to what we found in our, similar to what we did with our band pass active filter in the previous video, we would see that the magnitude at that resonant or that center frequency is RF divided by RI times 2 omega 1 divided by omega 1 plus omega 2.